Hello, everyone. Thank you for joining us for the Building Blocks of NB-IoT webinar, where we'll discuss DTLS, CoAP, OSCORE, and other important cellular IoT protocols. Before we get started today, a quick word about who we are. IoT is an award-winning IoT software company that enables organizations to quickly and efficiently manage their IoT devices. We make this possible through our commitment to interoperability and lightweight M2M. Today's speakers include David Navarro, who is our CTO and co-founder, and a friend of IoT, Akim Kraus, who is a CoAP DTLS cloud expert. During today's agenda, we'll cover major cellular IoT protocols available, the benefits and downsides to common cellular IoT protocols, and the protocols for specific use cases. A quick reminder about the way that we're going to schedule the webinar. The webinar will be recorded, and after the webinar, I will send slides and the recording of the webinar out to everyone who is registered. You may notice that all participants are muted, but we encourage questions, and I hope that you will send them through the Q&A, through the chat for the Q&A session, where we'll be happy to answer them. Okay, now I will pass the control to David, and he can discuss, to Akim, where he will discuss NBIoT and other protocols.
So thank you, Mackenzie, for the introduction. I would like to start with an idea that, or why we talk about Narrowband IoT and why it is something special. I think it's a problem, or it's an issue of a special purpose. And I think in Germany we have this very nice car. It's called a Unimog truck, and this is also a very special vehicle for a very special purpose. So usually, if you have something for a special purpose, this stuff is really great in this special purpose, but maybe weak in a general usage. So if you have this car, you know it's really perfect to drive to a very heavy terrain and to reach out very far away destinations. But if you want to use it to get for shopping in a city, I think it will not be the right one. So just keep in mind, a special purpose thing is not that good in a common use case as we would like to have it. So with that introduction, let's start. We will hear certain terms, and I would like to introduce them ahead so that it's clear what we are talking about. So we are mainly talking about Narrowband IoT. So it's a narrowband Internet of Things. It's just a cellular transmission protocol. Alternative ones would be LTE Cat1, LTE Cat-M, or GSM, the old ones. We will hear something about TCP/IP, just that everybody has the same understanding. This is the transmission control protocol. It's very common. And one of those features inside this protocol is that this protocol itself does do some retransmissions for you if some of the IP messages are lost. Then we have the UDP IP protocol. And here the point is that this protocol doesn't do this retransmission for you, but it assumes that the next protocol layer will do something similar and more efficient. So in UDP, they usually don't do the things because they assume that the next layer will do this better. We will have the TLS, the transport layer security. This is something like to authenticate and encrypt the communication over TCP. So authenticate means that we know to which peer we're talking, and encryption means that nobody else can decrypt and see the plain text. We will have DTLS, and this is simply very, very much the same as TLS for datagrams. And on the top, we will have the CoAP protocol, the Constrained Application Protocol. I think HTTP is very common, and CoAP is something like a binary HTTP over UDP. And especially we use this because this adds these retransmissions if some IP messages are lost. So that are the terms we are using in the next slides. So NB-IoT is a special purpose transmission technique. It was influenced by ideas like, what do we really need for something like a smart meter? And the idea so that we usually have smaller messages once a day or just a couple of hours. Small means not 10 bytes. I think it's about 100 or 200 bytes, the assumption that it works with message sizes of that, but it's not 20 or 100 kilobytes. We also assume that some of those meters will be mounted and located deep inside of buildings, which usually makes it hard to get a wireless communication there. And we also assume that such a device should last for very long and should not cost that much, because if you have so many devices in, that's very important to take care of the lifetime and the costs. So what does narrowband now do for these requirements? First, it offers a deep building penetration. So we have radio retransmissions, which helps us to reach that. We have narrowed bandwidth in the radio transmission, which helps us to go deeper inside buildings. Some modems offer us power classes to use, and sometimes we need better antennas. And if you want more, we have also some sources for these sayings. Just later on, you can go into more details there if you like. So the low energy consumption, it's also very good. So that for extreme conditions, especially in the deep buildings stuff, NB-IoT is the best in class of this technologies. And for the other environments, if it's not deep inside a building, it's more reachable, then it's still very good. So then there may be something better. So LTM takes a little less, but for it's still very good there. Just to say, if you're really deep inside the building, and if you're even if it's the best in class, it may take a little more than you assume, and in that cases it helps then to lower the frequency of sending messages. So maybe you can then switch to once a day or once every twice day. So the price, it's also said that narrowband IoT modules are currently the cheapest ones. It's said 5 to 10 euros. I think the cheapest one I found is something like 7 and 8 euros, and then you need also other equipment. So, but anyway, it's a little cheaper than LTM right now. And yeah, the SIM card prices are also relatively low because you don't need that much data, because you anyway cannot send that much data because you don't have the battery. So overall, if you take everything together, NB-IoT considers a lot, but mainly in the scope of this special use case that we want to have smart meters. So let's go. An application, in my opinion, usually does something like it sends from the device to the cloud some measurements, and optionally, occasionally, it sends back some processing status or configuration. So we usually have a message to the cloud and something back. So we have in the short introduction that narrowband IoT uses retransmissions and narrowing the bandwidth. This is mainly causes then also delays in the messages. So if you retransmit something, it takes longer. If you narrow the bandwidth, the band, you usually have a less bandwidth and it will take longer. So one problem of narrowband IoT is that it potentially delays your message exchanges more than you would like to. And so the next slides, they will show this effect on several protocols, UDP, TCP, and so on. And just to say, I did this, I think here in Germany, it's a quite usual condition that we have about minus 100 milledecibels. And if you do this, the measurements of the times were taken on the client side, so on the device side. But if you run the tests on your own, you will see that the times are always varying. So sometimes you have 2 seconds, in the next run you have 3 seconds, and so on. So this is varies, and it depends a lot. So if you do experiments, you basically need to do this multiple times and to take the average there. So let's start. So if we use UDP and over it CoAP, we have a very simple situation. So you remind that I introduced that we have basically some application data sent to the cloud. This is the first message here. And that we perhaps have then something back like the processing status, like here that it is changed. So in UDP, it's really that we have basically our application messages. If we use it in that combination, we have no security, so it's more for local and private networks. CoAP would add our reliability by retransmission. So if something is lost, then CoAP will retransmit this. And yeah, this is a case usually for simple use cases with limited transport layers. And I think Lightning systems are mainly using this. So the next one. So here we have a simple example for TCP. We see now a lot of more messages. So we have here at the beginning, we have the connect phase. Then here we see again our CoAP host message. This means this is our application message. Then we have again something, and then we have the response. So overall, we see a lot of more messages. This means, or this is caused by injection of control messages. So TCP wants to control the transmission, and therefore it injects additional messages. And the pain of those messages is that they also need to be transmitted over the wireless protocol, and that makes the times much larger. And you see it gets inefficient, or it gets less efficient than in the UDP case. So both we have seen is unencrypted, so it's usually more for like local or private networks. So what we now will see is what happens if we want to encrypt this. So usually we use TLS 1.2. Okay, that's currently shifting to 1.3, but still 1.2 is used a lot in embedded scenarios. So TLS usually uses a handshake. This is just a term for exchanging some messages ahead of such a connection. And in this handshake, we negotiate cryptographic parameters. For example, the cipher suite, which is used if it is ECDSA cipher suite or PSK or something like that. So you can negotiate a lot of things within that. The handshake authenticates the peers so that we know that we really exchange data with that peer and not with something else, and maybe with the wrong server. And we also negotiate then their temporary keys, which are then used for data encryption. DTLS 1.2 is then very similar to TLS 1.2. There is not that big difference there. It uses then UDP instead of TCP. So that's ahead. So for encryption, we need a handshake. And now we will see what happens. And yes, this is DTLS CoAP. So this is CoAP over DTLS over UDP. And I think the very first thing we see is that we now have the handshake. This is from the client hello to this finish message. And that's also quite a lot messages. So if we do this without advanced technologies, we will have always a lot of messages just in order to exchange then the application messages. These are two tools. Here we see also that 3 minutes later, we exchange the next application messages. You see this here in the time. Yes, that's possible, either if we are in a network where our addresses are not changing, or if we use some special extensions like DTLS Connection ID. With that, we have now security, so we can send our messages over public networks. CoAP is still adding reliability by retransmissions, so that's still important. And so this fits now simple use cases. I think for cloud metering or something like that, that's very important to have encryption if we want to send the messages over a public network. So here we use PSK authentication, and that basically also means that Wireshark can decrypt our application messages. Therefore, we see that we send a post and acknowledge. So this is now the TLS scenario. Here we use X509 authentication, and therefore Wireshark is not that easy to decrypt the application data. So we see the messages just as the application data. Yeah, compared to DTLS, we have still a couple more messages, because now we have the injected messages for the transmission protocol, and we have the TLS handshake. So we have a lot of messages to exchange just for those two application data messages. Okay, so that's what is commonly used in other scenarios, like the web. So HTTPS is using that, not with CoAP, with HTTP, but we see this has a huge overhead if we just want to send or exchange small messages. So yes, the sum up is handshakes requires many messages, and yeah, usually TLS is based on such that temporary generated keys are correspondent to your IP address, and depends on a lot of things. If this IP address changes too often, then you will have to frequently execute this handshake, and that's a large overhead. So especially for DTLS, there is an extension. That's what I have implemented. This is RFC 9146. It's called the DTLS Connection ID. This replaces the ID, the IP address, by an ID. And with that, we can reduce the number of handshakes significantly. So without this, we may use static addresses if we can do that. And if not, we have always the handshakes. In the TCP case, it's always the question how persistent our connection is or not. But for 200 bytes once a day, I don't think that a static TCP connection will work. I don't think that. So then you will always have to have the handshake, and with that overhead. So in my summary, I just counted the number of messages we need. So if we have the very simple case, UDP, CoAP over UDP, I assume 2% of lost messages. So we need to retransmit 2% of the messages. So we have 2.04 messages per exchange. So that's a very good result. For TCP, we have 3 messages for the connect and 3 messages for the exchange. So we have 6 messages at all. We see that this is straightforward. It has 3 times more messages. If we use DTLS, so with a PSK handshake, we have something like 6 to 8 handshake messages, and then we have the 2.04 messages for the data exchange. That results then in something to 8 to 10 messages. If we can use DTLS Connection ID, then we don't need the handshakes that frequently. So then it goes down to 2.04. So that's then again a great value. It's pretty much comparable to the situation without encryption. And in the case of TLS over CoAP over TLS 1.2, then we have 15 messages alone for the handshake. We have then still the 3 messages for the application exchange. And in totally we have 18. So I think we see here that from that to that, we can close to have 10 times more messages if we choose another protocol. So get back. So what are the NB-IoT pitfalls here? So I think we need to still consider that if we want to have this deep building penetration, this is considered to cause delay. So if you need more retransmissions on the wireless layer, if you have less bandwidth on the wireless layer because they narrow the bands, then you should consider that the messages will take longer. So, and if more messages you send over that protocol and they are delayed already in the radio layer, then this really tends to cause additional retransmission in the protocol layer. So you may remember those retransmissions are either done by TCP, by injecting additional messages, or those retransmissions are done by CoAP, if some messages are lost. But as more messages you send, you will also have more retransmissions in these protocol layers. And that increases the number of overall messages even more. So it's very important to consider those delays. If you don't, then this can also end up that your data exchange collapses completely, that it just sticks into retransmissions. So from my experience with Narrowband IoT, one pitfall I found is that usually if you want to send data out of the sleeping mode, going to the connected mode, this takes different times. So in good cases, it's up to 2.5 seconds, but there are also cases where it takes 50 seconds. And I think we also need to consider that we have here larger timeouts with a large variety. And even these times are usually larger than the common timeouts for some protocols. So for DTLS, such a timeout is specified by default by 1 second, and for CoAP, it's 2 seconds timeouts. So even if we use these protocols or other protocols, we need to keep in mind that we need to address the different times from Narrowband IoT. Maybe you remember now, special purpose means it's not good for a general case, and a lot of those timeouts are based on general assumptions about communication. But if you now use Narrowband IoT in order to have a better deep building penetration, then you need to address this different times. So for Narrowband IoT, there are solutions for those pitfalls. So the first thing is we should use a protocol which reduces the number of messages to a minimum. And in my consideration, this is basically that we can use CoAP over UDP, okay, if we have no public network, or we can use CoAP over DTLS Connection ID, or we can use CoAP over OSCORE. We will hear later for that. And this is mainly reducing then our numbers close to 2. So that's a very good idea to be used with the Narrowband IoT. Usually we should configure the timeout. So I use 3 seconds for initial timeout for DTLS and for CoAP. In my experience, the most libraries are able that you configure the timeouts there. At least the CoAP and the DTLS libraries usually come with that. And we also need to align either our transmission timeouts with the connection state if possible. So if the modem reports us it's connected or not, then we can start the timers. If we're not able to do that, we need to use a much larger initial timeout, at least to compensate such an initial connection time of 15 seconds, then we are easily and fast at an initial timeout of 15 seconds instead of 3. That's not the best solution. I tend more to take the connection state and then start the timers. That results in the end in a better communication. Overall, and just to remind, deep building penetration requires power. And if it takes too much power, then we really need to consider to reduce the overall number of message exchanges over the time. So if we're faced that it takes too much energy, we should lower down our traffic to once a day, once every 2 days, or whatever our application ID allows us. But that's very important. So deep building penetration is no free lunch. It costs something, and you need to compensate this with your application. But overall, if you take all these items here and consider them in your application design, then my experience is that narrowband really works very reliable and very efficiently, even if you have a very problematic radio situation. So just if someone is curious and wants to make also some experiments in a little faster way, I have a very small open source project for the device. It takes a Thinky 91 from Nordic, and I also use this open source server from Eclipse Californium. Yeah, I'm also the developer of both. And so if someone wants to make its own experience, in my consideration, it takes always an afternoon to get common with the client and to get common with the server. If you don't want to set up your own server, you can even use the Californium Sandbox server that's here. So it's only intended for very initial and very simple communication tests. There's no device management or something like that. It's just to see how much energy a message exchange will take, maybe with your modem, maybe in your situation. So, so what I did in order to demonstrate better what narrowband IoT means for different protocols is I made a small experiment. So what I do is I put my Thinky 91 in a steel cockpit. It's not. You should not take a too thick one. You need one in between because the point is, I have pods when you put in the Thinky, nothing works. I have pods if you put the Thinky, nothing changes. And I have some pods in between. And if you have some pods in between, then you will see that if your Thinky outside of the pod works, even with TCP, that's no point. So TCP also works under good conditions, but if you then put it into a bad conditions into the pod, and if you then close the pod with also a metal lid, then I was faced that I lost 20 decibel again, and with that my personal result was that if I use CoAP with TLS, so the TCP flavor, then this fails really quite often. And if you use it with DTLS connection and ID, then it really works quite often. So that's the difference. So maybe if you still consider to use that or that protocol, I think one of the ideas would just put your favorite protocol in a Thinky and then put it in the pod and then see if it works. So, and then report your results because I'm interested in. So I think I'm done. So I think we hand over to David.
Yes, thank you, Akim. So I'm here to introduce to you OSCORE, which is another security mechanism that you can use in the NB-IoT deployment. It is designed by the IETF and stands for Object Security for Core, which is the global group that at the IETF that design protocols related to the NB-IoT space. So first, let's talk about op-to-op and end-to-end security, which works DTLS and DTLS that Hakim brilliantly presented. What you have is security between two TCP or UDP endpoints. So typically your client and your server. But what was noticed and what is OSCORE trying to address is the case when you have some proxy in the middle, where the DTLS or TLS session ends onto the proxy before the data is forwarded to a server over another TLS or DTLS session, which means that the data sent by the client will be decrypted on the proxy. So if you remember when the Zoom software we are using now exploded, they were boasting about having end-to-end security. But soon people realized that you are actually one TLS session between you and the Zoom servers, and then another TLS session between the Zoom server and the people in your Zoom meeting. So defeating the argument of end-to-end security. And this is something, of course, that is now solved, and Zoom really have end-to-end security now. But this is the use case that OSCORE is aiming to solve. That is to provide a full security of your data between the client and the server. So from a network layer point of view, OSCORE is part of the CoAP layer. So it means it's designed to secure the CoAP message itself and not the transport. So it is really designed to be used with CoAP, not in the general case. And it can be used either alone as the only security layer, or it can be used in addition to DTLS or TLS, which is also a very common case. So with OSCORE, you have a security between the two CoAP endpoints and not between the UDP or TCP endpoint. So to explain how OSCORE works, let's just take a moment to look at what is a CoAP message. So inside a CoAP message, you first have an header, which contains mainly the code, just like the HTTP codes, GET, POST, PUT, or the response code, like 204 for change, 404 for not found, and so on, and the token, which is used to match a request and a response. Then you have the various options, like the URI path that you are trying to reach on the server, the content type of your payload, and so on. So where HTTP is using a text representation for all these options and the code, as Hakim said, in CoAP, all the header and the options are in a binary format to improve the size of the messages. And of course, you can have a payload also as part of the message. So what OSCORE is doing is from one CoAP message, it creates another CoAP message. But in this new CoAP message, some part of the of the original message are left as unprotected, so that the CoAP message can go through proxies and so on, and other part of the message are encrypted. So typically from the header, the code is encrypted. Most of the options are encrypted, and the payload is of course encrypted. And in the new message, you will have an header with a different code, just some of the option and an additional option, which is the OSCORE option used to indicate to the recipient how to decipher the message. And all the ciphertext is transmitted as the payload of the message. So if you take, for instance, a CoAP message, which is used to retrieve the temperature measured by a sensor. So as a code, you will have a get, a token, and some option, which are the URI host you are aiming, and the path on this host to retrieve the temperature. In this case, it will be /sensor/temperature. And the accept option is to indicate which is the format of the response you are expecting. And with OSCORE, this is converted to a new message where the code is a post, which is the same code for all OSCORE requests. From the option, we are just keeping the URI host option that will be used to for a CoAP proxy in the middle to be able to forward the message to the right host. You have this new OSCORE option that is introduced, and in the payload, encrypted, you will retrieve the original code, the option that were protected, and the option that were protected. In this example, there were no payload in the original message. So one of the advantages of OSCORE is the reduction in the overhead for the encrypted message that you will exchange. As you can see from the numbers here, there is a benefit on the overhead for the message compared to DTLS. But keep in mind that OSCORE was designed specifically for the CoAP use case, and so it can this is where it can benefit from that, whereas DTLS is used for the general use case. I cannot have such optimization. So the numbers may appear not that much for a benefit, but over the lifetime of the device, where typically a smart meter is designed to last for 10 years, in the end, the numbers are proved to be a huge benefit on the battery consumption of the device. So behind the scene for OSCORE, to protect all this data, both ends are sharing a common context. So the most important part of this context is, of course, the master secret that will be used to encrypt the data between the client and the client and the server, typically. So there are some additional data, like a salt, the various security protocols to use, and an ID of the context. But this part has default value and may not need to be provisioned on the device and the server. From this common context, both ends will derive a sender and a recipient context with their own ID and a security key for the session. So you will notice that there are two contexts which are mirrored on both ends. So the recipient context of the device A is the sender context on the server B. Same thing for the sender and recipient context. of the other part. So instead of having, well, it's like from the device, you will have two separate pre-shared key sessions between both ends. So for connection establishment, well, at the OSCORE level, there will be only one additional exchange. So the device will typically send a protected request with a chosen context ID. And from the server, this protected request, if matching the security context that was derived, will be challenged with a new value sent as the context ID. From there, the client will derive a new security context using the value provided in the challenge, and using another challenge value. And there it will protect this request with this new context, which hopefully will be accepted by the server, and the server will reply with the protected response to the initial request. So compared to the classical application exchange with one request and one response, here you will have one additional exchange to establish the security context in OSCORE. So all this seems nice, but actually OSCORE is not a full alternative to TLS and DTLS. So OSCORE provides for the security mechanism a pre-shared key mechanism, but it's lacking the raw public key or certificate mechanism that are more secure and allow for a more full-featured security on the device. OSCORE is also lacking a cipher suite negotiation and a Diffie-Hellman key exchange, so there is no real handshake with OSCORE. And more importantly, OSCORE does not guarantee a forward secrecy, which means that if one attacker were able to decipher one of the previous exchange between two OSCORE devices, they will be able to decipher any future exchange between these devices, even if new sessions, new security contexts were established. So to address these drawbacks, the IETF designed the EDOC, which is a new mechanism. So it means ephemeral Diffie-Hellman exchange for object, for constraint object. So it's a lightweight exchange, which is designed with OSCORE in mind. So it can be used in other contexts, but it's really designed for OSCORE. So with this handshake, now you will be able to negotiate the cipher suite in use, and all the context, security context data that will need to be provisioned on both ends with OSCORE can be negotiated during the first exchange. And EDOC also allow for the usage of certificates and raw public keys, but not pre-shared key, which is not really a problem because pre-shared key is already a part of OSCORE. One small drawback still at this time is that the EDOC specification is still a draft at the ATF, but it just yesterday it was sent for review to be published as an RFC. So the current text will not change, and we can hope for publication as an RFC for the beginning of the year. So with EDOC, of course, you will have a new handshake. So that means some more messages. So the EDOC will start by sending one message, which indicates who is the sender and what are the parameters they wish to use for the connection. This will be answered by the server with a new message. And if everything is okay, there will be a third message sent by the client to confirm the security session parameters. Message 4 is just here as an acknowledgement from the server. And from there, the device A can directly send a protected request to the server B, skipping the phase of security context establishment that is part of OSCORE. There are also work at the ATF to combine the EDOC message 3 with the protected request, which will mean that you will have only an additional 2 messages compared to directly sending the request. So OSCORE with EDOC can be considered a full alternative to DTLS and TLS, an alternative or an additional security layer, of course. So with EDOC, now you have access to the RPK and the certificate security mechanism. The cipher suites are negotiated. You have a real DTLS key exchange, and no forward secrecy is provided. So now I will talk about lightweight end-to-end. Because with what Hakim and I presented to you, with NBIoT, DTLS, and OSCORE and CoAP, so currently to use our devices as an IoT system, NBIoT is providing the transport. With IP, we have the addressing of individual devices. DTLS and OSCORE are providing the encryption and the authentication for the exchange, and CoAP is providing the messaging and the operation semantic in a RESTful way. But this may be not enough for a real IoT system. I will make the analogy with the mobile phone. So everyone has a mobile phone. You can individually address to other people in the world who have also access to a mobile phone. Hopefully your conversation will be secure. That's debatable, but let's assume that. But it is not enough to have a real exchange. First, what if I'm speaking French, and the people I'm calling is speaking English? Will not be able to communicate. And also, I will not be able to know what service the person I'm calling is able to provide. So if I'm looking for a plumber and I'm calling a bakery, even if we are speaking the same language, I would not get what I need. So we have a checklist of the IoT communication needs. First, you need a transport, obviously, to be able to exchange messages with the device. You need this exchange to be secure, which means encrypted for secrecy. You need to be sure that they are authenticated. Make sure that you are talking to the right device on the right server. And you need to make sure that everyone has the right authorization to do so. You need to define the operation semantic, or you will interact with the device in a RESTful way, in a SOAP way. But you will also decide how you will be onboarding a new device on your system, and all these devices will announce their availability. Once you have all that, you need to decide also how you will be encoding your data. Will your device send a JSON message? Will it be a raw value encoded as a float, or is it a text string, and so on? And what is the data model between two temperature meters? For instance, one can display directly the temperature, while the other one display the temperature and the unit and the maximum value that was measured, and so on. And you'll need also the discovery. So, or you will determine the capabilities of a new device that connect to your server. And something that is often overlooked is the device management, which is all you will configure and update your device during their lifetime, since smart meters, for instance, are designed to be deployed during 10 years on the field. So as we've seen, NBIoT answers the question of the transport. DTLS and OSCORE check the security box, and CoAP provide the operation semantic. And for the other checkboxes, one of the possible answers is lightweight M2M. So lightweight M2M is first a device management protocol that is designed by the Open Mobile Alliance, which previously designed the OMA-DM protocol for the mobile phone space. Lightweight M2M is tailored for IoT devices. And while being a device management protocol first, lightweight M2M provides all the other features that we are missing with just CoAP, DTLS, and NBIoT. And in that space, note also that lightweight M2M does not invent things, but more combine existing things like CoAP, of course, DTLS, OSCORE, NBIoT, and other standards like sensor markup language, JSON and CBOR, and others to provide a complete framework for IoT. And one of the additional benefits of using lightweight M2M, besides to not have to reinvent the wheel and design everything once again, is that you will have interoperability with other lightweight M2M systems, which means that you can use device off-the-shelf device from other vendors or connect to servers provided by vendors and don't have to develop your own server for this. Which leads me to one of our last slide, the product that we are providing at IoT Hub. We have two main products, Alaska, which is an IoT device management platform, that you won't have to implement if you go with lightweight M2M. This is provided as a platform as a service deployed in the cloud, available, of course, from any NB-IoT device in the world, which provide everything you need to manage such devices. And for the device part, we have the Iowa, which is an IoT client SDK, which allow you to provide all the functionality that we presented before in your devices, which Iowa being extremely compact from the code size point of view and from the power consumption point of view. And this is hopefully it's hopefully provide simple enough APIs that you can integrate it pretty quickly on your devices. The usual time to integrate that as a proof of concept in the first prototypes is usually in 1 or 2 days for customers. And such customers choose IoT Hub first because of our knowledge and our implication in all the standard bodies that defines CoAP, lightweight M2M, and so on, or agility, and they all praise our customer support for this. So with this, I guess we are open for questions.
Yes, Thank you very much, David and Akeem, for your presentations today. I hope that it was useful for all of the participants who are on the call. And from the participants, I have a few questions. For Akeem, the first one is, can you provide examples on how to align timeouts with the connection state?
Yes, I think it's easy. So usually your modem, that's my assumption. Usually your modem is in sleeping mode. And if you now send a CoAP message, then you can either start the CoAP transmission timeout when you hand over this message to the modem, or when you hand it over and then the modem tries to get connected to the network, when the modem reports that it is connected. So this means you either have also this narrowband time, which in my experience is something like 2 seconds, 2.5, or up to, in some cases, up to 15 seconds. So we have the phase where we don't change really data to the outside. It's just inside a narrowband IoT protocol used. And we either can put this time now to the CoAP retransmission time or not. And what I do is usually I take, if my modem provides me that, I take the time point when the modem says, yes, I'm now in the RRC connected mode, and then I start my timer. And with that, I have a better appropriate timing there. Does this answer the question?
I will go ahead and ask you the second
Okay.
question that we have from the same participant, which is, how do you read DTLS exchanges on Wireshark if you're using certificates?
I don't do this. With certificates, it's much harder. If you really want to read the exchanges with the certificates, I think you should ask such questions in the Wireshark community. There is a way, but it's not easy to reproduce, and so I don't do it. Therefore, if I just want to see and check the messages, I use PSK, and with PSK, it's much simpler because then it's simply configuring the DTLS protocol, and in that configuration screen, you see that you can enter the pre-shared key, and if you do that, then Wireshark is able to decrypt all messages. That's what I usually do. And then if I want to have real security or another security, depends on the personal preferences, then I use also certificates.
Okay, thank you. David, we have a few questions for you as well. The first question is, what is the computer overhead and memory footprint expected for OSCORE?
So the memory and RAM overhead is in the same ballpark as DTLS, I would say, because for the encryption algorithm, it's using exactly the same one as DTLS. And for the protocol part, the RAM size and the memory size will be smaller than DTLS, but not that much. So the bulk of the RAM and the memory and CPU usage will be taken by the encryption algorithm, which are the same. But maybe not for NB-IoT devices that tend to be really constrained, but most of the modem or SOC that we are using are also providing hardware security functions that can be used for the encryption.
Okay, thank you. Another question is it possible to run OSCORE on top of DTLS?
Yes, of course. That's one of the typical usage. So to the cost of some bandwidth and so on, but yes, it is totally possible. They are on different layers.
Okay. Sort of a follow-up to that is there a benefit to use OSCORE versus DTLS for the bootstrap procedure in lightweight M2M?
In the current state, yes, because DTLS allows you to use certificates, as in lightweight M2M, the bootstrap server is the most important server, since it's then configure on the device the security credential to use to reach the management server. That's the most important part of the security chain. So DTLS in the current state allow the usage of certificates or raw public key that are which are advised to use compared to PSK, because certificates provide the ability to more capabilities to authenticate the server and the device, and also allows to sorry, I can't find the English word, but certificates have an expiration date. So with this, you are sure that you are not talking to an attacker that has managed to retrieve old security information. And with certificates, you are sure you are talking to the right bootstrap server. But note that the communication with a bootstrap server usually happens once or twice in a device lifetime. So that's a trade-off which is beneficial to do.
Okay. We have a question about Iowa, and it's whether Iowa can be integrated with Nordic and Zephyr.
Yes, of course. Iowa is designed for all embedded platform, so you can deploy it from a small device like an AVR 8 platform up to a Linux, or even to a Linux platform. So even more, if you go to the IoT Hub GitHub, which will be fairly easy to find, you will find a light version of Iowa provided as an example, and you will also find additional repo, one of them containing a port to Zephyr, usable on a Nordic board.
Okay. The last question that we have is about Alaska, and it's, does Alaska provide an API layer?
Yes, of course. Since it's a platform as a service, you will on Alaska, you will have a graphical front end for human users, but the goal of Alaska is to be integrated with the customer application server. Alaska will take care of everything that is device management, data retrieval, but the analysis of the data, the usage for the customer use case, well, everything that is handled by an application server, and this application server will interact with Alaska over web APIs or other channel to convey the data, like MQTT brokers.
Okay, that's all of the questions that we have for today. Thank you again to David and Akeem for presenting, and thank you everyone for joining to the webinar independent of what time zone you're in. So we look forward to having you for another webinar, and we wish you a good day. Bye.
Bye.